from Professor Rose and category. I'm not even going to spend so I want to appreciate Prof for the foundation he has given us. The first time Prof taught me was when I was doing my master's studies. And I remember one point he made, which I will never forget. When he came to the class, the first course he taught us, so we were eager to see our results. So when Prof came to the class, he said, you know, when you are doing mathematics and some steps are missing, then some points are also missing. That's why in 711, some points were just missing and there was nothing left to add. I knew we saw our results already. So I went to Prof. I said, sir, what do we do so that we can have a very good result? He now told me some things, then I made a statement. I said, don't worry, I'm going to work very hard. He said, no. You can be working hard on the wrong thing. And that's, I never will leave it. And Prof may not know how that meant to me. I want to greet everyone, Professor Awu Bodema-Rensan, Professor Uyi Wandi. Thank you very much for coming. And I want to thank you, Prof. He has always been a mentor and has always been encouraging us. Where I want to talk about two things, and I'm just even going to talk about the basic area of those things because they have wide applications. For example, I want to talk about fuzzy sets, and then, of course, I'm very glad to hear about quantum mechanics, and it's even found that fuzzy set has applications in quantum mechanics as opposed to classical logic. That fuzzy logic would model quantum problems. Then I also talk about hyperstructures. Now, this I've worked more on fuzzy algebra before I started also moving with people who are in maybe electrical engineering or computer science to bring in some fuzziness into models. So what do we call fuzzy set? What's even the motivation for fuzzy set? For example, we know that usually when we have a set, classically, we can always say that an element belongs to a set or an element does not belong to a set. And with the modern trend in development in engineering and machine language and all of that, we run into some problems. For example, if we are to design a robot, maybe a facial recognition machine to save out fair ladies. The question is, how fair is the fair? So that's what brought in the idea of partial membership. So usually most of us will define a fuzzy set with a characteristic function, say mu from a set x to the interval 0, 1. And what this means is that if a set, for example, this set X will be a classical set, but a fuzzy subset of it will have this membership function. I'll give a very short example. So in that case, this, if A is my fuzzy set, so indeed A is a fuzzy subset of X. Okay? And it will have the membership function defined like this. And what that will mean is that I'm going to have membership value 1 when X is certainly in A. I'm going to have membership value 0 when X does not belong to A. And I'm going to have anything between 0 and 1 when X is partially in A. And of course, let me ask you, if I said you should list all natural numbers greater than or equals to 5, I guess everybody can do that. Starting from where? 1. All natural numbers greater than or equals to 5. No, greater than or equals to 5. Yeah. You know, it has to start from 5. Yeah. Our idea of where it begins is not the problem. Okay. We know it's going to be 5, 6, 7. Now, please take a piece of paper. Just please take a piece of paper. I want to give you another assignment. And let's see how our views agree. So we're going to write all natural numbers far greater than 5. So, and you know, in real life, when you are dealing with machines, When you're talking about a high temperature, low temperature, how low is the load? So what comes in when they design some of this machine now is fuzzy logic, fuzzy set, and the like. So that is one aspect I want to talk about. I mean, I just concluded now. The other part is hyperstructures. Actually, when I started working on fuzzy set, I got some review requests that has to do with hyperstructure theory. So apparently at that time, it was a new area for me. So, but I had to go and learn it. What is it about? And I discovered it very, very interesting. And it's also motivated by physical problems in physics. For example, particle theory, all this lepton and hadron and all of that. You know, in our usual group theory, we know that when we compose two elements, we have another element, talking about closure. But it often happens in physics that it's possible for two things to come together, it's rather a set. Okay? And people have worked in this area. It has been applied to inheritance, in genetics, in chemistry, in physics. There are so many hyperstructures. In fact, there's a paper I was just skimming through this morning. It's hyperstructure in physical particle physics. Particle physics. And it's talking about all this lepton and hadron and all of that, where there are collisions. When there are collisions of two different elements, and you don't just have one element, you have rather a set. Now, this has even gone far. Now we have hyperstructure theory in group theory, we have hyperstructure theory in ring theory, and there are so many applications in sister algebra, in binary relation, in graph theory, in hypergraph, and so many others. These are areas that people can work in. But often, I have rather worked in hyperstructure theory, especially relating to group theory, but I have done some applications with genetics, and the paper has been published. And of course, in the fuzzy set, there are so many applications. The first area that took me into serious application out of group theory was when I was going to China. I was invited for a postdoc in China, and my host asked me, can you learn LMI? I said, I'm already, of course, Nigerians are always willing to learn anyway we're going for a better. So I said, I'm ready to learn. So when I got there, he taught me, he was working in control theory. Precisely, he works in impulsive control theory. So I got interested, and then he introduced me to his model. And I told him that, but in real life, this thing cannot be precise. So there have been first work on that area. He introduced, because what they normally do is that when there's chaos, they try to find a constant matrix J, and then to introduce that J to bring a control. And he gave me an application in real life. And I said, look, this thing does not work in real life. And I gave him an example. If you go to the hospital, let's say you were sick, of course, because when my host taught me about chaos, one of the things he used is temperature problem. Like when you are sick, you have fever. It's a chaotic problem for you. Now, the question is that if the doctor recommends that you take injection 5 ml daily, the truth is that you actually get precisely 5 ml. What you get is around 5 ml. Because even if the nurse brings in 5 ml into the syringe, she cannot exactly give you 5 ml. So that becomes a fuzzy problem. So, and then he allowed me, I worked on the model, and then I made a presentation, and it was fine. And it turns out that 1001 of his own results, his own result was just 1 out of 1001 that we could get from the model that I did. And it was published in a very good journal at that time. So it became a motivation for his students. So even when I came back, we now have people working, using, trying to bring their model to bring fuzziness into it. So many of such things can also be used in physics. But I am still learning anyway. So it's just an introduction of what I'm doing. I work in hyperstructure theory, I work in fuzzy set. And I've also seen that even fuzzy set has a link with multi-set. And multi-set is used a lot in many of our, in many of our chemists. When you have all these machines, it's a multi-set. And the writing of the program is a multi-set operation. I've done a lot of work in that area, but not very much. Okay, thank you, because I said I'll use less than 10 minutes. So, comments? Do we have comments?
Okay.